Hello guys, nice to see you. How are you doing?
Hello, not bad. How are you?
Good, good. Friday. And
Good
this
afternoon.
hello. Yeah, weekend is coming, so should not be bad mood. Okay, so last time we discussed the intensity of sound. So we derived equations for the average power of sound, periodic sound wave, and also intensity of periodic sound wave. Um, so the derivation was carried out for a special case when we have one-dimensional situation. So the sound wave was spreading along some tube. Then we also considered the case when we have a point source of sound in isotropic environment, when we have some spherical spreading of sound waves. So if we want to determine sound intensity at some point at some distance from this point source, let's consider some distance r. So we need to divide the average power of our power source by the area of the sphere with the radius, which is equal to this distance from the point source of sound to the point where we want to determine the sound intensity. Now we will shortly also discuss such concept as sound level, which provides us in a bit more convenient way to deal with different sound, different intensities of sound which our ears can detect, because it's quite wide range of intensities, starting from something around 10 to minus 12 watt per square meter up to 1 watt per square meter. So louder we can detect, but it's just painful. So it's not anymore like hearing sound. It's just suffering from this extremely loud noise. Further, we will discuss Doppler effect. We'll consider mobile observer, mobile source of sound, and both observer and source when they can move in different directions, which with respect to each other, how it will affect to the so-called apparent frequency of the sound which observer will detect. And we will finish our discussion with the shock wave. It's the phenomena when sound is generated by the object which moves with a speed higher than the speed of sound propagation in this environment. So with this in plan, we can switch to our slides and start from sound level. So, as I said, there is some threshold for hearing with human ears, and it is considered to be intensity I naught equal to 10 to minus 12 watts per square meter. So we will specify here the frequency, so at 1 kilohertz. And we will discuss a bit later this moment in more details, because that's kind of important. But at this point, we specify to have some reference point. We specify, okay, for sound with frequency of 1 kilohertz, the hearing threshold is 10 to minus 12 watts per square meter. It can vary from person to person, of course, but on average, that is the case. And you see this is very low sound intensity, and it can vary in like actually up to this painful level, which is considered to be something like 1 watt per square meter. So it changes in the range of 12 orders of magnitude, which is huge. And in order to make it more convenient for to deal with, was proposed to operate with so-called sound level. So sound level is defined as follows: 10 multiply decimal logarithm of the ratio between sound intensity, which we experience, divided by threshold of hearing. So, for instance, if we consider sound intensity, which is at the level of hearing threshold, let's say I is equal also 10 to minus 12 watts per square meter. Then if we substitute it here, it will be 10 times decimal logarithm 10 to minus 12 divided by 10 to minus 12. So that will correspond to 0, because decimal logarithm of unity will give us 0. So it will be equal to 0. And it is measured in decibels. So 0 decibel means that sound is just at this hearing edge, that we barely can detect it. And obviously, if sound becomes more loud, like intensity increases, then in decibels, sound level will also increase. So for instance, if we consider sound intensity of 1 watt per square meter, that will be 10 times decimal logarithm of unity divided by 10 to minus 12. That will give us 120 decibel, because this decimal log will equal to 12. So 100 decibel is already painful level, sound level. And you see from barely hearing to painful sound level, we go only from 0 to 120, instead of going from 10 to minus 12 to unity. So it's definitely more convenient to operate with this, taking into account the wide range of sound intensity, which can be detected by human ear. Another important thing, which I mentioned that we will discuss, is how we, like our perception of sound with different frequencies. So it was shown that the perception means how we feel sound intensity depends on the frequency of the sound. So if we put frequency here in hertz, and here sound level, decibels, let us consider some semi-log scale. So it will be something like 20 hertz. Here will be something like 1000 hertz. And here, let's consider 20,000. So first of all, as you know, human ears can detect sound waves only in certain frequency range, which is between 20 hertz and 20 kilohertz. So we don't hear any so-called infrasound and ultrasound. So within this range, it's also frequency dependent, our perception. So as I mentioned, the threshold of hearing 10 to minus 12, which corresponds to 0 decibel, it's here, 0 decibel, is reached at 1000 hertz. However, if we go further to the left or to the right, to lower or higher frequencies, this hearing threshold will increase. So for lower or higher frequencies, we will require higher sound intensities than 10 to minus 12 watt per square meter in order to hear this sound. So that's why we will have something like this. Goes like this. So apparently the sensitivity of human ear is highest for the frequency of 1 kilohertz. That's why we need the lowest sound intensity in order to detect this. However, for lower or higher frequencies, our sensitivity drops and we require higher intensity of sound or higher sound level. So there is another interesting feature. If we deal with very loud sound, which is, let's consider here 120 decibel, which is at this edge of painful feeling, then our frequency dependence, like frequency dependence of the sensitivity of human ear, becomes frequency independent. So what does it mean? That here at very loud sound, it doesn't matter at which frequency this sound is generated, we will perceive it, like feel as the same, sorry about this. We'll feel this sound intensity the same way for 1000, 5000, or 300 hertz. So that is the feature what is observed when we deal at very high level of sound intensity, and that's something when our like ears as sensors for sound waves are going to some saturation regime when intensity is so high that it doesn't matter anymore at which frequency you feel it as very extremely loud, equally loud sound. However, when we deal with very low sound at the edge of hearing, there is a clear frequency dependence of our detecting capabilities. Okay, so now let us switch to the Doppler effect. So before we start, let us consider this system. We have some axis X. We have, observer here. Here, let's have source. So if observer is moving towards the source in this configuration along axis X, so V observer is larger than 0, so it's positive. If observer is moving in the opposite direction, then V observer is negative. So the same we can write for the source because it also can move. So if it moves away from observer in this configuration, that will be V source larger than 0, positive. And here, if it goes towards the observer, V source will be negative. Okay, keeping this in mind, because later it will be convenient to remember this arrangement. We consider first case when we have stationary sound source and mobile observer. So we have some sound generated by this sound source with the following parameters: some frequency f, some wavelength lambda, and there is environment in which this sound is propagating with the speed v. So this is speed of sound. Now we remember that frequency is defined as speed of sound divided by wavelength. So our first case, we have stationary sound source and mobile observer. Let us consider it moves towards the sound source, so we have positive velocity of observer. And in this case, frequency which will be heard by observer, some apparent frequency, will be higher than the real one. So why? Let us show it. So instead of v in the numerator here, for the equation for frequency, we should put now v plus v naught, because we move towards the source of sound, so we approach it. So the respective speed of sound to the observer will be speed of sound with respect to the source plus speed of observer, because we are approaching the source of sound. So that will be v plus v naught divided by lambda, wavelength. So lambda in its turn can be defined as speed of sound divided by frequency. So let us substitute it here. It will be v plus v naught divided by v divided by frequency. And if we rearrange it, so it will be v plus v naught divided by v times initial, original frequency of the sound. So now we see that numerator is larger than denominator because we have v in both, but in the numerator also v plus v naught. V naught is positive in this case. We observer is approaching the source of sound. That's why we can write that apparent frequency of the sound will be higher than the original frequency of the sound. So if we have the case when observer is moving away from the source, we will write the following. It will be apparent frequency is equal to v minus v naught divided by v times original frequency of the sound. Now our numerator is smaller than the denominator, and for this particular case, apparent frequency will be smaller than the original frequency of the sound. Okay, now we consider another situation when we have stationary observer and mobile source. So with this, we can write that lambda prime, the detected wavelengths, apparent wavelengths, will be equal to original wavelengths minus some change in wavelengths, delta lambda. So that is case when we consider that source is approaching our observer. So that would be written as original wavelength lambda minus v source. Instead of delta lambda, we can write v source divided by frequency of the original frequency of the sound. So now, if we again mention about the relationship between wavelengths and speed of sound and frequency, as we have shown here, we can substitute. So we can express the apparent frequency, which stationary observer will hear, f prime, as v, speed of sound, divided by lambda prime, which is the apparent wavelength of the sound generated by mobile source approaching the observer. So in this case, we will have v divided by lambda minus v source divided by f. Lambda we can also express in terms of speed of sound and original frequency of the sound. So that will be equal then v divided by f minus v source divided by f. Now we take out from the parentheses this f, and we have the following. Will be v divided by v minus vs, source of the sound, which approaches observer, and in this case, as you see, it is negative, times frequency f. So in this case, we see that our denominator is smaller than numerator, and therefore our apparent frequency, which observer will hear in the case when source is approaching the observer, which is stationary, will be higher than original frequency of the sound. If the source is going away from the stationary observer, so moves along axis x, then we need to change sign from negative to positive. So f prime will be equal to v plus vs times f. So in this case, denominator is larger than numerator. So f prime will be smaller than original frequency of the sound. So now we can combine these two options of mobile observer and source. So in that case, we need to be careful with the signs and put appropriate signs. But let's say if we are interested for the situation when observer and sound source are moving towards each other. So imagine this situation. If we come back here, oops. So if we come back here, observer is moving towards the source and source is moving towards the observer. So both are moving. So in this case, the frequency, apparent frequency, which will be detected by the observer, will be given as v plus v naught divided by v minus vs, and that times original frequency f. So if we change the directions of observer, like motion of observer or source, we need to pay attention to these signs, to put appropriate signs, and this equation will give us the apparent frequency, which is different from the original frequency because of Doppler effect. So with this, we are also done. So we have some time to discuss shock waves. So shock waves, yeah, you have a question? Sure.
In the first case, V naught is the velocity of the observer, or?
Yes, we know its observer. Vs is the source of sound.
Or what about V? Is this
V
yeah.
is the speed of sound in the environment.
Thank you.
Yeah, okay, you're welcome. So let us maybe delete this part. Don't need it anymore here. And shock waves. So that's kind of interesting also effect. And it is observed when the source of sound, which creates this disturbance in the air, for instance, moves with speed higher than the speed of sound. Usually it's not the case. We usually experience in everyday life speeds which are lower than speed of sound because it's quite high speed of sound in air. However, super sonic planes or bullets, they fly with speed higher than the speed of sound, and as a result, we experience some so-called shock wave. And let us try to see why it is formed and how we can quantify it. So for this purpose, let us consider how we get this cone, like Mach cone. I'm sure you have seen it many times, but not all of you have seen how you draw it from scratch. And I believe that it could be useful. If you haven't seen that, that could be useful for better understanding where it comes from. And that's why let us do it here. As accurate as possible with my not so great drawing skills, but I will try. So let us assume the situation when we have the speed of the source twice larger than the speed of the sound. So, and also we will consider some time interval of 5 seconds. Now you will understand what I mean here. So that will be our axis X. Here is position of our sound source. Can be bullet, can be plane, whatever. Let's call it sound source. At time 0 second, so it's initial moment of time. Then let us consider distance which sound can travel per 1 second and put it here. So let's say this is distance along axis X, which sound can travel in 1 second. So maybe let us put it a bit shorter because then it would be too large scale. Let's do it like this. So if sound can travel in 1 second this distance, then our source can travel twice larger distance because its speed is twice larger. So it will, in 1 second, our source will be here. So now if we divide our axis in 10 these equal segments, so we have 1, 2, then we have 3, 4, 5, 6, 7, 8, 9, 10. So at second 2, our source will be here. Second 2 second. At second 3, it will be here. At second 4, it will be here. And at second 5, it will be here. So now, so at each point where it will pass this source, it will generate sound wave. And if we consider sound which was generated at this point at 0 second, at second 5, it will have 5 seconds to spread the sound. And we know that one of this segment is the distance sound can travel per 1 second. So means that in 5 seconds, sound can travel 1, 2, 3, 4, 5 up to this point from 0.0 second. So in order to make it more convenient to draw, let us make also axis y and try to put here the same intervals. 3, 4, 5. So that is also distance to which this sound generated by the source when it was in point at 0 second will reach at that moment when the source will be here after 5 seconds. So now let us draw kind of a circle around this point at 0 seconds. And that this circle, it actually will show the in all directions the distance to which the sound generated at this point will reach after 5 seconds. So if we consider point at 1 second, then it will have only 4 seconds until the source will reach final point at 5 seconds. So that's why it will move not by 5 segments, but by 4 segments. So it will be 1, 2, 3, 4. So it will reach here. And from here, it will be 1, 2, 3, 4. So it will reach up to here. Again, we can draw here a circle. Now we move to point at 2 seconds, this one. So it will have only 3 seconds to, the sound generated at this point will have only 3 seconds to travel before our source reach final point at 5 seconds. So that will be 1, 2, 3. So it will reach up to here and here, 1, 2, 3. So we will draw smaller circle, and here will be 1, 2, 3 also. Yeah, like this. So at 0.3 second, there will be only 2 seconds to travel. So 1, 2, it will travel up to here, and 1, 2 will travel up to here. So we can draw now this circle. At 0.4, it will have only 1 second to travel. So we will have very small circle here. And at 0.5, we will not have any circle because at 0.5, our source just reached to this point and generated sound didn't have any time to spread in the environment. So now what we can do, you see, if we, from this final point at 5 seconds, draw a line which is kind of tangential to all these circles which we draw, it will show us the geometric configuration of points to which along this line, so sound generated at any point from 0 to 4 seconds will reach simultaneously. So that will create some front of the shock wave, and this shock wave will be kind of comprised in some cone, because here we will have also such tangential line. So this is cross section, we see triangular, but in three-dimensional case it will be cone, because in three-dimensional these are not circles but spheres, and this cone is called so-called Mach cone, and that's how we form the shock wave when the sound source moves with higher speed than the speed of sound in this environment. So now let us try to get some quantitative analysis done of this Mach cone. First of all, we are interested in this angle. Let's put point A, point B. So next to this point B, on the top of the cone, we are interested in this angle alpha. And maybe I can change the color so we can see something here. If we put a perpendicular from point A to point C, so here is right angle, we can write the following: that the distance from point A to B, A, B, is equal to V source times delta T. So delta T is, in our case, delta T will be 5 seconds, but it doesn't matter. We just needed to draw it, but further it will cancel out. From the other side, distance between points A and C, AC, is equal to V, speed of sound, times delta T. It's kind of a radius of this sphere, which is created by sound generated at the point 0 second, at the first initial position of the sound source. So now, since ABC is a right triangular, we can easily determine alpha. So sinus alpha will be equal to hypotenuse, which is AB. Sorry, it will be this opposite cutted AC divided by hypotenuse AB. AC divided by AB, that is equal to V divided times delta T divided by VS times delta T. So that is V divided by VS. And this can be represented as 1 divided by capital M. So first of all, this angle is defined only by ratio between the speed of sound and speed of our source. And there is some parameter which is called Mach number. M is equal to V source divided by V speed of sound. So this number, capital M, gives us the factor by which the sound, the source is faster than the sound in the environment. So keeping this in mind, so we know now at which angle this Mach cone is formed. So at which angle shock wave front is approaching the observer. So we can use this information to deal with some problems which are focused on the shock waves. So with this, I would like to finish our discussion of sound. If you have any question, you are welcome.
How to write Mach word?
I believe it's Mach like this.
Oh, thank you.
Sure, maybe double check it.
Thank you.
You are welcome. So I hope it was clear. And one thing, when you see this image with circles, but that's definitely more clear when you draw it from scratch. And in textbook, unfortunately, you cannot see the process of drawing. So it's the last final image you can see only, but that's better for understanding. And probably you will keep this in mind for a long time, how this shock wave is formed. If you haven't been already, if it hasn't been clear for you previously. Okay, guys, so with this, we actually finish our big part of mechanics discussion. And starting from next week, we will deal with thermodynamics and molecular physics. And we will start a new topic, quite big. So congratulations with finishing the mechanics part. And have a good weekend, get some rest, and see you healthy and happy on Monday.
Thank you.
You're welcome. Bye-bye, guys.
Thank you. Bye.
Thank you. Goodbye.
Bye.